All right. Calc BC, Unit 1, Assignment 6B. This is log 1, the second one for that day. So here are your graphs. Check them. Pause it if you need to. Number 5 looks like a lot of fun, huh? All right. The other questions on that page, here they are. Some domain questions, which logs are infamous for. Okay, and then next page, solving log equations. Pause it if you need to. Check your answers. No calculators. And down here, you can use calculators on these. So check them. Pause it if you need to. Okay. So now we're going to go ahead and go over these. So first one. So a lot of times what I like to do on these is to graph their inverse function first, because those inverse functions are really easy. So the inverse function would be y equals 2 to the x, which would go through 0, 1, horizontal asymptote, y equals 0, and would look like this. So the log, corresponding log function, for vertical asymptote, x equals 0, x-intercept 1, 0 instead of y-intercept, and look like a reflection across y equals x. So, I don't know. That's how I do it. Increasing, concave down, range, negative infinity, positive infinity, asymptote, x equals 0. So, there you go. This is just log base e of x. So I would graph e to the x. Goes through 0, 1. Horizontal asymptote, y equals 0. E to the x. And I'd flip it, press y equals x. And I get x-intercept 1, 0. Vertical asymptote, x equals 0. And the graph would look like that. Arrows in the ends. Approaching the asymptote, not crossing, not going away. This is increasing. Concave down. Range is negative infinity, positive infinity. Asymptote is vertical line. So it needs to be the equation vertical line. X equals 0. Okay. So if they don't show a base on the log, then that's log base 10. So I'm going to go ahead and graph 10 to the x. Does all the normal things. So this is 10 to the x. Then we're going to flip it across y equals x. Vertical asymptote x equals 0. X-intercept 1, 0. So that's log. The 2 multiplies all the y values by 2, which it's hard to tell here, but it's going to make it look taller, I guess. The minus 3 moves everything down 3. So 1, 2, 3. The point that I ask you to keep track of is going to be 1, negative 3. And the graph, I guess, just looks steeper here. Doesn't have to be perfect. Should go through that dot though. All right, so this graph is increasing, concave down, range is negative infinity, positive infinity, asymptote is x equals 0. Okay, So this, I would do y equals 1/3 to the x, which I would do 3 to the negative x. So, 3 to the x looks like that. The negative gets flipped across the y-axis. Then to do the log version, I need to flip this across y equals x. Now these ones get a little weird. Has a vertical asymptote, x equals 0. Has x-intercept, 1, 0. But it's gonna look upside down like that, and then the negative of that flips it upside down, and it kind of looks like a normal log graph. So this is increasing, concave down, range is negative infinity, positive infinity, and the asymptote is x equals 0. All right, save the best for last. This one looks like a crazy one. So I'm going to do e to the x first. So that's e to the x. I'm going to flip it across y equals x. Like I've done many times. So that's natural log of x. The minus 2 on the inside moves everything to the right 2. So now vertical asymptote is at x equals 2. Intercept's at 3, 0. Right? The negative on the inside flips it upside, or the negative on the outside flips it upside down, and then the 3 moves it up 3. So now that point I'm asking to keep track of is at 3, 3. Yeah, oops, and I'm keeping track of the wrong graph. It's supposed to be the upside down one. Forgot about that. Gets a little crazy sometimes. It's hard sometimes to remember which one was your last one. So that is decreasing, concave up, range is negative infinity, positive infinity. The asymptote is x equals 2. So there we go. Got a bunch of good graphs. Now for some domain problems. So the domain logs, the inside has to be positive. I want the final answer in interval notation. So that one's done. The inside of this one needs to be positive. Write it down. Show me the work. Don't put the greater than right here. That looks weird. Makes me think that you think natural logs have to be positive, which is not true. 3 positive infinity. All right. The inside of the log, the minus 3 actually doesn't even matter. So that's going to be 0 to positive infinity. Oh, shoot. There's another part of the problem. So that's the domain. B says for what values of x is the function less than 0. So that's a separate problem. So that's where you'd exponentiate both sides and say x is less than 1. Okay. But then you need to combine that with the domain. So let's label this. This is the domain. This is what you get. They have to both be true. You could do 2 line checks if you want. Open circle at 1 or the left. Open circle at 0 or the right. And where they overlap is your answers, 0 to 1. Which also, by the way, makes sense because this is what the natural log graph looks like. And we're saying, where is the natural log graph less than 0? Well, that's right here, 0 to 1. Okay. This one, where is the whole function less than 0? Well, exponentiate both sides. X minus 1. X minus 3 is less than 1. E of 0 is 1. Oops, I messed that one up. Oh, no, I did it right. Getting confused. So x is less than 4, but it also needs to be greater than 3. So, I mean, I think you could do that in your head if you want. It's between 3 and 4. So this is the domain. Let's label the domains. This is the domain. So then I want to know, where is this less than 0? Well, I would move the 3 to the other side first and then exponentiate both sides. So x is greater than 0, but less than e to the third. So it's going to be between 0 and e to the third. I mean, you can do a line check if you want, but that's up to you. Okay, next one. Domain is the inside has to be greater than 0. So this is a rational inequality. We've done these a lot. Line check. Open circle, open dots. Test a value. X equals 4 is true, false, true. So the domain is negative infinity to 0, union 3 to positive infinity. So this is the domain that you were asked specifically for. Tricky part is when they don't say anything about domain, you got to realize it. Now, where is this function less than 0? Exponentiate both sides. X over x minus 3 is less than 1. This is another rational inequality, but you want to bring everything to one side. Compared to 0, you want to give these the least common denominator. So it's going to be x minus x, 0. So we're going to get 3 over x minus 3 is less than 0. So x equals 3. Line check, open dot 3, test. X equals 4 is false, true. So where do these overlap? Well, this one's to the right of 3, this one left of 3, but this, I think these parts right here, from negative infinity to 0, they overlap. That's your answer. This one right here, let's see, domain, the inside needs to be positive, factor it, it's polynomial inequality, we do a line check, find the roots, simply line check, these are open dots, test the value, x equals 5, true, false, true. So the domain is negative infinity to 0, union 4 to positive infinity. That's the domain. Then we gotta say, well, where is this negative? Exponentiate both sides. X squared minus 4x is less than 1. Polynomial inequality, move everything to one side. And then we can't factor that, so it's going to get a little messy. We're going to do quadratic format. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. 2a is 1. So it's going to be positive 4 plus or minus 16 plus 4 is 20. So that's 4 plus or minus, take square root of 4 out, it's going to be 2, and there's a 5 left over. So we're going to get 2 plus or minus root 5. So one of these is 2 plus root 5, and one of these is 2 minus root 5. I had to estimate these because you're going to do a line check. So root 5 is between square root of 4 and 9. It's between 2 and 3. It's really close to 4. So I'd say like, I don't know, 2.3. So I'd say this is about 4.3. And this is about negative 0.3. So when you do your line check, these are going to be open dots. And use the exact values, 2 minus root 5, 2 plus root 5, and then test a value. I'm going to test 5, which if you go up here, it is 25 minus 20 minus 1 is positive, which is false, true, false. So we got to combine the domain with where the solutions are, which is about negative 0.03. So it overlaps a little bit right there. And it overlaps a little bit right there. So the answer is going to be 2 minus root 5 comma 0 union 4 comma 4 2 plus root 5. That's the final answer. So You could make the line checks right above and below each other if that helps, and use the estimates. I don't want those estimates in your answer. That can be in your work to help you. Okay, domain inside has to be greater than 0. Find the roots. X equals 0 at 0 plus, we're going to do degrees, 180 degrees K. So X equals 0, 180, 360. Do a line check. 0, these are open dots. And we're going to test the value. X equals 90. Uh, 90, sin 90 is 1. So 1 is greater than 0. True, false, true, false. So the domain is 0 to 180. And then to solve it, you would exponentiate. We'd say less than 0, exponentiate both sides. You get sine x is less than 1. So you say, well, when is x equal to 1? 90 degrees plus 360k. So x equals 90 degrees is the only time. So we do a line check for that. 90 degrees. Test a value. X equals 0. Sine 0 is 0. True, false. So where does this overlap with that? Well, looks like 0 to 90. And yeah, 0 to 90. So ooh, I missed something. This is bounce. This is where the graph bounces off the graph, right? It's 1. So when 0 worked, this works also. So this is actually part of it also. So it's going to be, and I put brackets on this, which is weird. It should be 0 to 90, parentheses, union 90 to 180. That's the answer. Got to watch out for that. Bounce off the graph. Okay. So, solving long equations. We did a couple together. On 13, 14, we already did. Just demonstrating the two main strategies here. It's either to get a single log equals single log so that their insides equal, or a log equal to a single log equal number, and then change the exponential notation. So here, we're going to combine these together by multiplying them, and then 6 equals x. Done. We did 13 and 14. This is a log equal number. It's all ready to go, so I would change the exponential notation. X to the 3/2 equals 8. And then to get x by itself, you raise both sides to 2/3. So that the 3/2 and 2/3, they multiply each other with exponent rules. Now here, I would do the cube root of 8 first and then square it. Cube root of 8 is 2, squared is 4. Okay, change this one to an exponential equation. And then that's pretty much the answer, except that we can write it nicer. So this is going to be the same thing as 1 over 27 to the 2/3, right? Which is 1 over 27 to the 1/3, and then squared. So cube root of 27 is 3, squared is 9. So x equals 1/9. Okay, there's a couple different ways to do this. You could say e to the x equals e to the 1/2. Set the exponents equal to each other. They have the same base. Or you could say natural log cancels out of e and you get x equals 1/2 right away. It's up to you. Here, 3 to the -4 equals x. So this x equals 1 over 3 to the 4th. So x equals 3 squared is 9, 27, and 1 over 81. Next one, I'm going to combine these logs. So you got to bring this in first. So it's going to be log base of 2 to the 4th, which is 16, divided by 3. Then we set the insides equal to each other, and We're done. This one, we want to combine these logs together by multiplying their insides. And then we're going to rewrite it in exponential form. So base is a 10. If you don't see base, it's a common log. So 10 to the 30th equals x to the 5th. Now, instead of trying to figure out what 10 to the 30th is, why don't we just raise both sides to the 1/5, fifth root, and then use log rules here. And so exponent rules, x equals 10 to the 6th. Now that's a lot easier. That's x equals 1 with 6 zeros. 1, 2, 3, 4, 5, 6. 1 million. Okay, you got to bring this in. So then we can divide x squared to the 3rd power. And then we can simplify this. X to the 6th. So it's 4 over x to the 5th equals 2. So x to the 5th over 4 equals 1/2. X to the 5th equals 2. So then we take the 5th root of both sides. No plus or minus, it's the odd root. So x equals the 5th root of 2. Or 2 to the 1/5. Okay, we're going to bring those numbers in first. Now, what we could do is we could say, okay, well, that's going to be x to the 6th times 3x divided by x to the 4th. We could do it, we could combine 3 of them together at a time if you want. I'd simplify this. This is going to be x to the 7th. This is going to be 3x cubed equals 10. So x cubed equals 10/3. We're going to take the cube root of both sides. So x equals either the cube root of 10/3, or I could break it up, cube root of 10 over cube root of 3. We could rationalize the denominator. If you do that, you can multiply with the cube root of 9 because you got to get a perfect cube. So then that would be the cube root of 90 over 3. So there you go. All right, 23. Now, even though we're using a calculator, we might just wait till the end to use it to get a decimal answer. But if you can't make the bases the same, like we did on the previous assignment, then you want to use log, natural log, log of any base. Log base, regular log works really well here because that's a log base 10. And log base 10 and 10 to the x are inverse functions. They cancel each other out and get x equals log 2, which is, on your calculator, 0.310. Okay, same thing here. Log 5, 3, the x minus 2 equals log of 3. Now, the reason we do this is because the things that are stuck in the exponents have variables in them, then you can move them in front using the log rules, right? And you got to put in parentheses if it has multiple terms and stuff. So at this point, it's kind of up to you. We could divide the log 5 to the other side, and then add 2, and then divide by 3. So that would be x equals log base 3 over 3 log 5 plus 2/3. And we calculate that 0.894. You could have distributed the log 5 and then solved for the x. And the only difference is you would have log 3 plus 2 log 5 all over 3 log 5. It would be the same answer, except just combined to a single exponent. Here now, natural log would be really good to use here because it'll just give you a cleaner answer. You could use regular log base 10 if you want. But here those cancel out. For x equals natural log of 100 plus 1 divided by 4. X equals natural log of 100 plus 1 over 4, which is, on your calculator, 1.401. 0.401. You can use regular log if you want. It'll look different, but your decimal should be the same. U.S. national debt is modeled by 0.0515, 1.131 to the x, where x is the number of years since 1900. When did the debt first reach $1 trillion? Okay, well, first of all, 1 trillion. Let's see if we can do this. That's a million. It's a billion. It's a trillion. So we can start with that. And then we're going to just solve for x. So before you want to undo things backwards, reverse order of operations. So we're going to divide both sides by that. And then we're going to take the log of both sides. And then we can move the x in front. So it's a coefficient. And then divide both sides by that. So x equals exactly log of 1 trillion divided by 0.0515, all divided by log of 1.131. So that's the exact answer. Now we get 248.551, but that's the number of years since 1900. When would mean we should add 1900 to this and say 8, 4, 11, 20 in year 2148. Now I think we're well beyond trillion already, so instead of writing all these zeros, you could write 10 to the 12th, in your answer. So, okay. There you go.